Knowing the equilibrium constant for a reaction can help predict the following features of the reaction. 1. The tendency of the reaction to occur, but not the speed, right? It just tells us the tendency, right? Are we going to form products? Are our products favored? Doesn't tell us how fast we're making them, right? There's like our diamond. Oh, well, that product of graphite is favored, but it's not happening real fast. Whether a given set of concentrations represents an equilibrium condition, and the equilibrium position that will be achieved from a given set of equilibrium concentrations. All right, so there's 3 things we can learn from that equilibrium constant. So a value of K that is bigger than 1 means that at equilibrium, the system will consist mostly of products. Equilibrium lies to the right, and the reaction goes essentially to completion. A very small value of K means that the system at equilibrium is going to consist mostly of the reactants, and that the position is far to the left, and the reaction does not occur to any significant extent. Doesn't mean it's not important. They mean statistically in a sense of magnitude of numbers. We're going to do a lot of stuff with solubility and with acid-base chemistry that is going to tie into some things that have very, very small equilibrium constants, but they're still really important. The size of K and the time required to equilibrium are not related. Just because you've got a big K doesn't mean you're happening fast. Well, let's do a concept check. If the equilibrium lies to the right, the value for K is large, or bigger than 1. If the equilibrium lies to the left, the value of K is, small, or less than 1. Right? Let's look at this reaction quotient Q. So the reaction quotient Q can be calculated at any point using that same formula where it's products over reactants. Doesn't necessarily mean it's equal to K. So remember, you can always calculate a Q. K is that special condition when we're at equilibrium. It helps us to determine the direction a system will shift, towards the products or towards the reactants, when all the initial concentrations are non-zero. If something is 0, right, if you start off with 0 products, you know you have to form products. If you start off with 0 reactants, or one of your reactants being 0, you know it has to go back form some of those reactants. Okay? It's obtained by applying the law of mass action, using initial concentrations instead of the equilibrium concentrations. So it's using whatever arbitrary concentrations they give you. For ammonia synthesis, where we've got nitrogen and hydrogen forming ammonia gas, our Q value is just going to be products over reactants with the appropriate coefficients, either 2 or 3. If Q is bigger than K, the reaction will proceed faster in the reverse direction. The products are going to decrease and the reactants will increase. If Q is less than K, the reaction will proceed faster in the forward direction. The products are going to increase and the reactants will decrease. If Q is equal to K, you're at equilibrium and there's going to be no change. If a reaction mixture contains just the reactants, then Q is equal to 0 and it has to go in the forward direction because K is always going to be positive. Right? The kind of center point you're thinking about for K is 1, right? If it's bigger than 1, right, really big number, then it's going to go forward, favor the products. If K is small, right, less than 1, but not negative, it's going to favor the reactants. If the reaction contains just products, then Q is going to be at infinity, and the reaction is going to proceed in the reverse direction. All right. So here's an example of looking at this in terms of concentration, whether you're Q or K. So our calculated value here. So if we're looking at a relationship between Q and K and the direction of the reactant. So right here at 1.5, that's our K value. Right, that's in here. So when Q is equal to K, there's no change. If Q is less than K, right, I don't have a lot of products. I need to make more. Things are going to move forward in the forward direction to the right direction. If Q is bigger than K, so if my numerator is bigger than my denominator, relatively speaking, I need to make that numerator smaller or my denominator larger or a bit of both. I'm going to take some of my numerator, throw it on the denominator until I reach K. I want that equilibrium value to be reached by consuming something to make something else. So let's look at an example. We're going to use this reaction quotient. For the synthesis of ammonia at 500 degrees C, the equilibrium constant is 6 times 10 to the minus 2. We're going to predict the direction in which the system will shift, either towards the reactants or towards the products, to reach equilibrium in the following 3 cases. And they're going to give us concentrations of the ammonia. This is our product. And these guys over here are reactants. Right? So 3 different conditions for our products and our reactants. Which way is it going to shift? Well, to do that, we're going to need to calculate the value for Q, which is just products over reactants. So in case number 1, we're going to plug in the concentration of the ammonia and the concentration of the nitrogen and the concentration of the hydrogen, right? Making sure to raise to the appropriate exponents based on the stoichiometric coefficients, right? Because this guy was so we've got N squared and 3 hydrogens and 2 ammonias. Since K is 6 times 10 to the minus 2, Q is bigger than K. To attain equilibrium, the concentrations have to be decreased, the products have to decrease, and the concentration of the reactants increased. System is going to shift towards the left, right? We're going to consume some of our product, and we're going to backform some of our reactants to bring that quotient, that ratio, that fraction back into what the value for K is. So then we'll do it for B. All right, same idea. We're still going to do products over reactants. All right, making sure we exponentiate properly based on the balanced chemical equation. And we get 6.01 times 10 to the minus 2. So Q is equal to K. There's going to be no change. All right, if we calculate under condition C, again, products over reactants, exponentiated properly, plug in the right values. We get 2 times 10 to the minus 3. Q is less than K. So the system is going to shift to the right, and we're going to form more products. We're going to make our K is our products over our reactants. And if this value Q is too big, or sorry, if Q is too small, then we need to make this guy bigger, and we need to make this guy smaller. A typical equilibrium problem involves finding the equilibrium concentrations or pressures of the reactants and products given the value of the equilibrium constant and the initial concentrations. There is, of course, an easier one, that is, here is a series of concentrations or pressures. The system is at equilibrium, calculate K. Then it's just products over reactants, right? That's pretty easy. Nobody ever has problems with that. It's just, you got your balanced chemical equation, you got your expression for K, products over reactants, you plug it in, you get the number. The harder one is what's going to happen if you're given a K and some concentrations. How are you going to calculate that? Right? So dinitrogen tetroxide in its liquid state was used as one of the fuels in the lunar lander for the NASA Apollo missions, and it decomposes into gaseous nitrogen dioxide. So we got our reactants, and we got our products. If we consider an experiment in which gaseous N2O4 was placed into a flask and allowed to reach equilibrium at a temperature where our Kp is going to be 0.133. Just looking at this, we know that if K is less than 1, we're going to favor our reactants more than our products. At equilibrium, the pressure of N2O4 was found to be 27 atmospheres. Calculate the equilibrium pressure of the NO2 gas. Very standard question. You should be able to do something like this, no problem. I'll put a little bat in here for one of our BATs, right? Because this is something that you're going to want to be able to do pretty proficiently. Right? That's most of what the problem solving is going to be like in this chapter. Right? So we know that the equilibrium pressure of the gases of the NO2 and the N2O4 have to be equal to 0.113. So we've got this equation for K. We're given a specific number. We've got our pressure of our NO2 squared and our N2O4. Right? We're going to rearrange it. We're going to multiply each side by the partial pressure of the N2O4, and we're going to divide each side by 0.113. So we'll say that our Kp, our partial pressure of the NO2 squared is going to be Kp times the pressure of the N2O4. So 0.133 times 2.71 is equal to 3.60. So that's our partial pressure of the NO2 squared. We need to get rid of that squared. So our partial pressure of the NO2 squared is going to be the square root of 0.360, so 0.6. Right? Not too bad, right? All you did is you plugged in the numbers and you solved for the missing one. Let's look at another example. At a certain temperature, a 1 liter flask initially contained 0.298 moles of phosphorus trichloride and 8.7 times 10 to the minus 3 moles of phosphorus pentachloride. After the system had reached equilibrium, 2 times 10 to the minus 3 moles of chlorine gas was found in the flask. The gaseous phosphorus pentachloride decomposes according to the following reaction. We got our PCl5 decomposing into PCl3 and 2 chlorine gases. So we got to have our balanced chemical equation. We're going to calculate the equilibrium concentration of all the species and the value of K. All right, a little bit more work involved, but still not bad. We're always going to start out the same way with our products over reactants. To find the value of K, we have to calculate the equilibrium concentration of all the species and then substitute those back into the equilibrium expression. By beginning with the initial concentrations, which we'll define as the concentrations before any shift towards equilibrium has occurred, we're going to then look and see how they change. So initially, we had no chlorine. And initially, we had 0.298 moles in 1 liter, so we had 0.298 molar phosphorus trichloride, and we had 8.7 times 10 to the minus 3 moles per liter of the phosphorus pentachloride. And so we're going to do that math and end up with 8.7 times 10 to the minus 3 molar. So we've got 1, 2, 3 concentrations. Remember, we've got K is going to be our products over our reactants, right? We know the concentration of all of our products and all of our reactants when we start. Find the change required to reach equilibrium. Since no chlorine gas was initially present, but we did have some at equilibrium, we had to have gained some chlorine. And where would that chlorine have come from? Well, the only place it can really come from is from this decomposition of phosphorus pentachloride. So we're going to decompose some of our phosphorus pentachloride and make some more chlorine gas. Right? So 2 times 10 to the minus 3 moles of our phosphorus pentachloride must have decomposed to form the 2 times 10 to the minus 3 moles of chlorine gas. And we're also going to make an additional 2 times 10 to the minus 3 moles of the phosphorus trichloride. So to reach equilibrium, the reaction shifted to the right. It had to because we had no chlorine. There was no choice. So we needed to decompose some of our pentachloride, and we're going to gain, a little plus symbol, 0.2 times 10 to the minus 3 moles of the phosphorus trichloride and the chlorine gas. Remember, this guy was given, and we just kind of figured this out. Right? How did it need to get there? We're going to apply this change to the initial concentration. So we lost some phosphorus pentachloride, and we gained some chlorine, and we gained some phosphorus trichloride. So our concentration at equilibrium is going to be 0 plus whatever this change is. And 2 times 10 to the minus 3, so this gives us our concentration of our chlorine. Our phosphorus trichloride, we started off with 0.298 molar. We're going to gain 2 times 10 to the minus 3 molar. That gives us 0.3 molar. And our phosphorus pentachloride, our reactant, we started off with 8.7 times 10 to the minus 3. We're going to lose, so minus 2 times 10 to the minus 3 moles per liter. And we're going to get left with 6.7 times 10 to the minus 3 molar. Now that I have each of these things, I can plug it back into my K expression. We've got a Cl2 concentration, a phosphorus trichloride, and a phosphorus pentachloride concentration. Put in the numbers we just calculated from before, and we're going to find our numerical value for K. All right, pretty straightforward, right? Let's look at another example. If we got carbon monoxide reacting with steam to produce carbon dioxide and hydrogen at 700 K, the equilibrium constant is 5.1. We're going to calculate the equilibrium concentration of all the species if 1 mole of each component is mixed in a 1 liter flask. So I'm going to start off with our BCE. That's our balanced chemical equation. And that's going to let us, as soon as you get a balanced chemical equation, right, you can go straight to this, right? Your balanced chemical equation, and those two things immediately follow on after each other. And so we know it's going to be products over our reactants, and we were given a numerical value of 5.1. Our initial concentrations for everything, it said, was 1 mole of each in that liter. So the initial concentration of each of these things is going to be 1. That's easy math there, because Q is going to be the concentration of each of these things in moles per liter. So 1 times 1 over 1 times 1, which is 1. So Q is less than K. It's not initially at equilibrium, and it's going to have to shift to the right. So we're going to move our reaction to the right, and we're going to form some of our products. So before we start with the initial concentrations and modify them to obtain the equilibrium concentration. So we're just saying, okay, at equilibrium, we know we've gained something, we've lost something over here. Just apply those numbers to the initial concentrations like we did in the previous example. The system we know is going to shift to the right to obtain the equilibrium condition. This is going to tell us whether we're going to add or subtract to our reactants, or whether we're going to add and subtract to our products. So let's assume that, let's call it X moles of carbon monoxide must react for the system to reach equilibrium, which means that the initial concentrations of CO will decrease. We're going to lose some of our initial CO. Right? So at equilibrium, our concentration of carbon monoxide is equal to our initial minus some small amount X. Since each carbon monoxide molecule reacts with 1 water molecule, the concentration of the water vapor is also going to decrease by X moles per liter. So we have our equilibrium concentration, and that's going to be our initial concentration minus our change. All right? And this X is going to be the same for each, for the CO and for the H2O. As the reactant concentrations decrease, the product concentrations are going to increase. They're going to go up. Since all the coefficients are 1 in the balanced chemical reaction, 1 mole of CO2 is going to react with 1 mole of H2O, and it's going to produce 1 mole of CO2 and 1 mole of H2. Or in the present case, to reach equilibrium, X moles per liter of carbon monoxide will react with X moles per liter of water to give an additional X moles per liter of carbon dioxide and X moles of H2O. So here we've got this another balanced chemical equation waiting for your input. And so how are we going to balance this out? Well, the initial concentrations of the CO2 and the H2 will increase by X moles per liter. So we're going to gain some CO2 and we're going to gain some H2. Now we have all the equilibrium concentrations defined in terms of the initial concentrations, what did we start with, and X, what our change was. So we've got all of our initial concentrations over here. That was super easy. That was all 1. And then we're going to change, right? We're going to lose a little bit of our 2 reactants, and we're going to gain a little bit of our 2 products. So at equilibrium, all we're doing is just taking column A and then combining it with column B. Right? So at equilibrium, it's 1 minus X and 1 minus X for our 2 reactants. And for our 2 products, it's going to be what our initial concentration was, plus X. We're going to gain some CO2. We're going to gain some H2 gas. In this example, the system is going to shift to the right, so the product concentrations increase and the reactant concentrations decrease. So if Q was in the other direction and we're moving it towards the left, we would subtract from our products and add to our reactants. Also note that because the coefficients in the balanced equation are all 1, the magnitude of the change is the same for all species. Right? If we had a 2 in there, we would lose like 2x. We're just going to multiply x by 2. Since we know that the equilibrium concentrations must satisfy the equilibrium expression, we can find a value of x by substituting these concentrations into the expression. So we're going to take and substitute our new value for x, or a new value for CO2, involving the x's in there, and we'll get 0.1, so we'll get 1 plus x squared divided by 1 minus x squared. Since the right side of the equation is a perfect square, the solution of the problem can be simplified by taking the square root of both sides. So we get 5 is equal to 2.26, which is equal to 1 plus x over 1 minus x. Multiplying and collecting the terms gives x is equal to 0.387 moles per liter. Thus, the shift in the system is to the right, and it's going to consume 0.387 moles per liter and 0.387 moles per liter of H2, and it's going to form 3.87 moles per liter of carbon dioxide and 0.387 moles per liter of hydrogen. Now the exact concentrations can be calculated, so we've got our value for x. All they're doing is going back a step, right? Plugging in for x. At this 0.387, because remember over here we just had 1 minus x. The values can be checked by substituting them back into the equilibrium expression to make sure they give the correct value for k. So if in doubt, test it out. Right? Plug in the specific numbers in here. Right? Make sure you get the value for k out that you should be getting out. This result is the same as the given value, 5.10, within round-off error. So the answer is most likely correct. Let's look at another example. Assume that a reaction for the formation of gaseous hydrogen fluoride from hydrogen and fluorine has an equilibrium constant of 1.15 times 10 to the 2. Big K, bigger than 1, right? Mostly going to form products. And fluorine has an equilibrium constant of 1.15 times 10 to the 2 at a certain temperature. 3 moles of each component is added to a 1.5 liter volumetric flask. Calculate the equilibrium concentration of all the species. So the first thing we need to do is we need to figure out our initial concentration. So our K value is going to be products over reactants. We're going to get this balanced chemical equation to give us the K values. And we got to figure out what the concentration is for each of those. So we're going to do 3 moles divided by 1.5 liters, right? That was part of our setup, a 1.5 liter flask and 3 moles. Right, so we're going to 3 over 1.5 and we get 2 molar for all of the concentrations of each of the species. Our value of Q, we're going to calculate the same way as we do K, products over reactants. We're going to plug in our specific values, 2 squared over 2 times 2, because there's just to the first power here. So we're going to get 2 squared over 2 times 2, which is 1. Q is much less than K, which is like 100 something. So the system has to shift to the right to reach equilibrium. To determine what change in concentrations is necessary, we're going to define the change needed in terms of x again. So we're going to solve for what that change value is. We're going to let x equal the number of moles per liter of H2 consumed to reach equilibrium. Stoichiometry of the reaction shows that x moles per liter of fluorine will also be consumed, and 2x moles per liter of HF will be formed. Right? So if we're decreasing our H2 by 1, we're decreasing our F2 by 1, but we're making twice as much F, so this guy HF, so this guy's going to be 2 times X. Okay, so the stoichiometric coefficient here determines what we do with X over here. So if we look at our little table, right, we've got our initial concentrations here, and we've got our change as minus x, and plus 2x, which means that our equilibrium concentration is going to combine those. So 2 minus x for our hydrogen, our fluorine is 2 minus x, and our HF is going to be 2 plus 2x. Right? And these concentrations can be represented in a shorthand table as follows. These are sometimes called ICE tables or IDE, where there's an I and a delta for change and an equilibrium. It just helps organize your thoughts for what are you doing with these, right? So your initial line here, right? You're going to take your initial concentrations and put them in the initial line. Your change, you say whether you're going to gain or lose, that's going to go on this line. And your equilibrium is just going to show you what's happening here. And learning how to work these ice tables is a skill, right? You will get good at it. We will give you lots of different ice tables, right? Sometimes you have to puzzle around with how are you going to work this, but this ice table is an incredibly useful tool. Okay. So to solve for x, we're going to substitute our equilibrium concentrations into the equilibrium expression, right? So we were given this value of 1.15 times 10 to the 2 is equal to hf squared divided by H2 times F2, right? So this is coming from our balanced chemical equation. This guy here would have had to have just been given to you. Right? And we know that our concentration of HF is 2 minus 2x, and our concentration of H2 is going to be 2 minus x, and our concentration of F2 is going to be 2 minus x. So really they're just grouping these guys together. So they had a 2 minus x for the H2, and they had a 2 minus x for the fluorine, and they just combined them to this. Right. The right side of this equation is a perfect square, because we got a squared up on the top and a squared over here. So we're going to do the square root of both sides. Take a square root over here, and then we'll take a square root of this guy. And we're going to get the square root of 1.15 times 10 to the 2 is equal to 2 plus 2x divided by 2 minus x. Again, this if you got that calculator with the solver, it's going to make your life so much easier. Right? This isn't too hard to do. Right? We got to rearrange and solve for x. X is going to have a value of 1.528. Right? But if you can do that using your calculator and not having to do that algebra, it's going to go faster. Therefore, our equilibrium concentrations for our hydrogen and our fluorine are going to be 2 molar minus x, or 0.472 molar, and our HF concentration is going to go up by 2x. This is going to be 2 plus 2 times 1.528, and we ended with 5.56 molar. Checking these values by substituting them into the equilibrium expression gives a value which agrees with the given value of k. So we're going to take these guys, put them back into our equilibrium expression, should be able to get k back out. That's kind of a nice little double check.